Right, cool. Welcome to my workshop, Teacher Sensors New Tricks with Machine Learning. I'm doing this live, as you might have noticed from the first 5 minutes. So we're actually going to build a machine learning model and run that on a small sensor, and then stream the results of that actually to the Things Network. So pretty cool. Naturally, there's hardware involved, there is networks involved, so it's a bit exciting to actually do this live, but very confident about that. So yeah, I hope that people saw my session from yesterday. So I have a very, very long history with Things Network. Back in 2015, when Johan and Winke were just literally kind of envisioning this idea of building a global distributed network for IoT devices. When it was still kind of a pipe dream, I was already sitting with Johan and Winke in a bar talking about literally that, and seeing how much it has grown. Last year, especially, I mean, if you're at the live conference and there's 1,500 people sitting in that room watching you talk and watching the ecosystem grow, I think it is super powerful. So this year, unfortunately, a little bit different. But yeah, so for me, kind of where I feel that IoT devices get really valuable is when they kind of see on this kind of junction of real life and technology. So being able to sense what is happening in the real world. And IoT devices typically promise that, but they don't always deliver. Kind of, as I said yesterday, the number one example that people still build is, oh, what is the temperature? And okay, sure, that's a valid use case, but it's not a very interesting use case. There's a lot more things around us in the world that we can perceive as humans, where it's really easy, where I as a human need to say, okay, what is happening? Because I have vision and I have ears. So I can actually listen or see what is happening and tell you, where a sensor has lots and lots of problems doing that. So all of these devices that we deploy, there's a lot of them. I think Winke said they doubled traffic over the last 6 months, which is absolutely amazing. But I want to build something more useful, more interesting, and stuff that can actually determine its place in the world a lot better. So what are we going to be building today? We're going to be adding vision to our LoRaWAN sensors. So these are two examples of things in the community that do something similar. So been talking quite a bit with the guys from Q42. So they have connected camera traps, currently relaying data over satellite. Talking a little bit, how can we scale that down and make that smaller, which I think is really great. And for us also, something what Adam Benzian has been talking about earlier in the conference is the involvement that we had together with a bunch of other partners in the TTN ecosystem around Elephant Edge Conservation Project. And some stuff that we want to do here is, for example, when do we see an elephant on a thermal camera? When do we see a poacher in a place where that's not the case? It's really hard to determine if an elephant is walking somewhere if all you have is off-the-shelf sensors like temperature or even basic accelerometers. Whereas but if you have a thermal camera and you have a human looking at it, it's very easy. It's like, okay, that's probably an elephant. Okay, cool, send it over. So let's take that human out of the loop and replace that by, an actual smart sensor. So I don't know if you guys can see my camera at the moment, but I brought this, an elephant. So I have also mounted a camera here on my desk. So that's coming from Arduino, actually. So Arduino released this yesterday, or announced it yesterday. The vision shield for the Arduino Portenta. It's their new microcontroller in the Pro line. It's a really nice dev board. It's incredibly powerful, but still being able to run really low power as long as you go into deep sleep after enough. So we have that board literally mounted to my desk here. You can see the camera feeding a little bit. I classify an image. So the main purpose here is, do I see an elephant, yes or no? We check, what do we see? Has the conclusion changed? If so, then we relay it to the LoRa radio and you drop it down at the Things Network. Super easy. So what we're doing today requires the Portenta H7 and the LoRa Vision Shield. So these are available as of today. We would love to We would have loved to send a bunch of these over for the conference, but we're not available yet. But you can actually follow along with this workshop if you don't even have that. So to do that, find 2 objects in your room or 1 object in your room that you want to detect. Then sign up for free at jimples.com. Then click this little button, let's collect some data. And then click the show QR code button for your mobile phone. And that transforms your phone into a smart sensor where you can collect data and then finally run that model as well. The natural part, it's going to be a bit harder for your phone to send anything to TTN. But the model that you actually train translates well onto other devices. So the final model that you have can actually run on a wide variety of dev boards, not just the Portenta, but also on the OpenMV boards that they've released, a bunch of ST boards, and kind of anything with a C++ compiler. So if during the workshop you want to do something here, just do this and use your phone to start building a model. So, and I also need to look at the chat at the same time. So if I'm looking to the left, it's not being rude, just looking at that. All right, so here at my desk, I have the Portenta H7 mounted. And this is my Edge Impulse project. So this is the place where we acquire data, first of all. Then we design a machine learning model. And then finally, we deploy that back to the device. And everything starts with data. So what kind of data do we need to collect here? Well, naturally, this sensor or machine learning model has no idea what an elephant is, let alone what a stuffed animal or a stuffed elephant is. So we need to tell it that. And we do that by collecting a whole bunch of photos and just labeling that this is an elephant, this is not an elephant. There's naturally unlimited classes that you can do here, but we're going to limit ourselves to 2. And if you have the Portenta shields, then it will look like this. So this is our data acquisition UI. The Portenta runs some firmware that we developed that makes it really easy to both see what is happening as well as to grab data from the sensor straight away. So typically really hard. I mean, this device does not have a screen. There's no buttons on it, anything where you can easily snap some photos, let alone a little LCD display to preview what is happening. But you can see that straight here in the UI. If you do this on your phone is the viewfinder as well. So straightforward too. So this is my living room. There you can see my hand, not staged. And yeah, let's slap a couple of photos of stuff that is not an elephant. So definitely not elephant. My hand, also not an elephant. Water bottle. And as you can see, right, so this is a few photos that I'm actually collecting. Data acquisition for these types of problems is often a thing where you're going to spend most of your time. Not just because data acquisition in general, takes a lot of time, which it is, but it's also you need to create a certain type of data. It needs to be clean. It needs to be labeled correctly. And that is relative then. And it needs to be kind of, it needs to be representative of the problem that you're actually trying to solve. And yeah, that means that if you try to do detect cameras from thermal images somewhere on the savannah, that means that one, yeah, someone needs to install those cameras. And then second, someone needs to actually label all the data and say, yeah, this was an elephant, yes. And this wasn't. Cool. Yeah, if someone has an OpenMV camera and want to do something, just Google OpenMV Edge Impulse and you get the tutorial on how to do data acquisition. But it's in essence just go to the dataset editor, collect some data, and then say send to Edge Impulse. Super easy. All right. So now we have some unknown data. Then we're going to need the elephant here as well. So let's label that. Elephant. Cool. And actually, elephant can be in a whole bunch of different positions. So it's falling over. And different locations. So cool. All right. So in total, I did a bit of pre-work. naturally. So far we've collected 39 photos of not elephant, 34 photos of is elephant. And we also have a test set. So when we're building an ML model, you want to divide your data set in kind of two. A training set, where we actually use to refine kind of this formula that we try to find when building this ML model, and a test set. So that's data that the model never sees during training, and you can use it to validate your data. So we split that up already. It's a little bit unbalanced. If you want to swap that over, so for example, you've collected hundreds of photos in your training set, just hit the rebalance data set button, and we swap those out in a sec. So yeah, if you have the Portenta, Hank, there is this repo, example Portenta LoRaWAN, on a Impulse. There's a button here that leads you to this page. And at this page, you'll find the firmware. You just load it in a sec. Yeah, Sebastian, if you have a phone on you, then go to Edge Impulse, sign up, click Devices, connect a new device, and select your phone. And if you have a Portenta board on you, you can just you can find this page and go from there. So I'll be able to follow that. So we'll have in this case, let's say 70 photos here, and we got about 34 photos here. And let's actually do something with this, and let's learn from that. So the first thing that we need to do is kind of manipulate our input data to make sure it's actually going to be able to run on device. And the biggest trick you have here, because if you want to run this on a microcontroller, you have limited compute power. This dev board is really powerful, but it's still a small microcontroller underneath. So the first step that we try to do here is resize this data to something that is good enough for your use case, because the bigger the image, the larger the ML model is going to be as well. So that we do here. So we resize this image actually to 64 by 64 pixels. That might sound small, but you can have a pretty interesting still set of features where you can recognize that. We'll see that in a second. From there, we then want to do some pre-processing on this data. For these images, there's not a lot that we need to do, but you can, for example, combine an object detection algorithm or a computer vision algorithm to find the interesting object. So what the guys at OpenMV have been doing around that is, for example, do face detection first. So you detect the face first, and then you only run the machine learning model on that part. So you can do some pre-processing here. And then we want to have a machine learning model. So we come with a bunch of presets here. The one that we're going to use here is a transfer learning model. So what we do here is that we've already trained a machine learning model on lots and lots of data, specifically focusing on things that image models need to determine or need to figure out. Then we strip off some of these final layers, and then we retrain that with your data. The benefit that we have there is that we need relatively little data. The model that we have here is about 100 photos in total. That is very, very little for an ML model. And still get relatively good performance even in the field. So let's get the image. So as I said, we don't really do much processing except that we resize the 64 by 64 pixels. We do that by cutting off the sides here. And then we reduce the color depth to grayscale, because this is a monochrome lens actually. And as you can see, I mean, you would think 64 by 64 pixels, that is very little. But you can still pretty much still discern that there's an elephant in these photos and that there's definitely not an elephant in these photos. So that's great. Naturally, we also show directly what the on-device performance is going to be, because we don't want to have people building models that are not going to fit on their device in the end. But here, because we do so little, just reducing the color depth, we need a few milliseconds of processing time and barely use any RAM here. So let's save that and let's generate some features. So what we then do is we're going to give you insight in how well your data set separates. And we do that even before we throw any machine learning at it. So what we do here is we take all the data in your data set, resize it, So then we have a 64 by 64 pixel image. And then for every single one of those items in your data set, we try to lay them out in the 3D grid in a way that they're as far as possible from each other, depending on how well they look alike. So this is my whole data set. In orange, you see all the data that is unknown. So that was not an elephant. And in blue, we see all the data that is an elephant. So with this, we can spot issues with our data set relatively quickly. So if data is close together, but there are different colors, that is a bit suspicious. So let's look at that. So that's me. And yeah, I don't know why the model thinks this is weird, but at least this is an indication that this is something where we actually want to take a look at. So definitely stuff where stuff comes here from the left. So both of these actually have my foot in it. So that's why it's grouping it together. But relatively clear what we have here. So this is a good indication that what we're going to train here in the little sack is probably going to work quite nicely. So from there, let's train a ML model. What you try to do when you train a machine learning model is, I said it yesterday in the presentation, it's just a different way of writing your code. If you write code normally, you have data in, the values from your sensor inputs, and then you have rules. So a rule might be if the sensor value is above a certain threshold, then do X, and if it's below that, then do Y. If you don't know those rules, then machine learning is a really inefficient way of finding those, because you say, okay, this was my input, this is supposed to be the output, try to find the hidden correlation between these for me. That takes lots and lots of compute, because the model doesn't have any of the contextual knowledge that we have about sensors and what machines do. But it's a really nice way of finding this hidden correlation, because if I give you a 64 by 64 pixel image, and I give you 100 of them, and I tell you, okay, write me an algorithm that's going to determine if this is an elephant, yes or no, you're probably going to approach it in a way of, okay, well, I need to, I try to detect it as like a gray blob somewhere, but then someone throws like my bag in here as well, which is going to be really, really hard. This model doesn't perform so well. Interesting. Let's actually take a look. So we've trained this model. It doesn't work too well. I'm not entirely sure why. But fortunately, I have a trained model that works a lot better before I added these last 3 photos. So what we can do here is we can go into this data set and look at which ones were actually classified incorrectly. So once again, we have kind of a nice way of showing, okay, what is happening and where is it misclassifying. For example, this photo has a lot of trouble actually figuring out what this actually is. So it might be because we're too far out of frame, or I do indeed look like an elephant, Johan. Thank you. Or maybe it's my leg in here, something like that. So this might be an indication that we actually want to go into the sample, change this around a little bit, or actually remove this from the sample. What we do on device is going to be, we don't trust a single frame, because as you see, it actually might be incorrect. Some stuff is classified as elephant, but then the next photo, which is really close, so this one is classified incorrectly, this one is classified correctly. So kind of the trick here is never to trust any single reading. So what we do on device is we look at the last 10 photos that were made, and if 7 out of the 10 are actually think that it was an elephant, but at least 70% confidence, that is the moment we actually flag it like that. Let's actually test out how well our model works straight here. So once again, I see my camera feed here. I click start sampling. I grab a photo, and now we ask the model to classify this. So unknown, that is great to know. We can also see kind of what are the samples that look most like this sample in here. So this is one of the samples that actually looks a lot like this, which makes sense. It's almost the same photo. So we try to help and guide you a little bit in evaluating why a model makes a decision and what is happening underneath. at all times, because in essence, you're putting in a black box. You say, okay, the model has found a formula for me that maps this nicely from A to B, but how well do you actually know if that works, yes or no? Let's actually try it with an elephant as well. So this is definitely not going very well. Let's try that with the light a little bit changed. So one of the problems we have right now with the Arduino, with the Portenta, is that there's some exposure issues, which you already see. And that changes every time that we reset the camera. So let's actually get a model now. God damn it. Fortunately, I loaded a better model on the device already. Thank you, Johan. So let's hope that this actually works better if I re-plug the device. So now we actually have an elephant. I'm going to restart this device in hope that we fix our exposure issues. All right, so now the exposure is at least a little bit different, which is interesting. Yeah, this is my last shot, and then we're going to throw this on the device. Johan and I have been doing lots of workshops in our day. So here we go. Actually, good exposure, elephant, 100%. So cool, we have a model that seems to work, at least if we don't have overexposure. So let's actually put this on a device and start classifying stuff on this sensor and send it over to TTN. So the way that we do that is we can create a C++ library from here, and that packages up all the code, all the signal processing code, all the neural network code, etc., and turn it into a really simple, quick library that we can integrate in virtually anything. So this runs on a wide variety of Arduino boards. It runs on the OpenMV camera. It runs on the new Portenta. It runs on embeddOS, Zephyr, etc. And even on Linux if you want to integrate it that way. So we have our example application here, the example Portenta LoRaWAN. I saw that Ajit already shared that earlier. So if you want to run that here, you just drag the Edge Impulse SDK folder, the model parameters folder, and the TF Lite folder. So yeah, this also runs on the ESP32 cam, but it's relatively slow. So you can drag all of these in here, and then write some code to just interact with the sensor like you would with anything else. So we have an event here, the event change call, and that happens when we see something else happening in front of the camera. So stuff that can come out from here is elephant, unknown, and uncertain, if we are unsure what we're actually looking at. And uncertain is when we have, uncertain typically happens between state changes. So elephant was there, now the elephant is not there. Because then you might have a couple frames where we saw the elephant, a couple where we didn't see it, or we don't have enough confidence to actually set this as or actually trigger this as a proper event. So yeah, a little bit of logic that we put around here to talk with the LoRa radio on the Portenta H7. So we have our modem, we join over OTAA to the things stack v2. So I'm very sorry for using a deprecated service when I was logging in this morning. And then we just look at, okay, did we see an event that changed? And was it at least 7 seconds? Because we're on data rate 5 as of 7, so we can send about every 7 seconds. In that case, we just send the current event over port 3 directly to the network. So straightforward. So as said, we don't trust a single reading. So we have some parameters here to play with. So we say we want to do 10 readings. So we look at the last 10 frames, and we do about 10 frames a second. 7 of these need to be the same, and we need to have at least 60% confidence in a frame before we trust it. So you can play around with that a little bit to prevent false positives. For From here we can build, or we can just flash. Stop this. All right, and let's open the TTN console. And let's open a serial monitor to the dev boards. So we're joining the network. And here on the right, you can see what the camera currently thinks it's seeing. So at the moment, our prediction is that we are unknown, which is naturally, and that is actually being sent to the network. Now let's try this with the elephant. Elephant. Not elephant. Cool, awesome. That works, and actually sent it over to TTN for immediate classification. And it's, yeah, so definitely multiple objects. Alexander's question is definitely possible. This is a 2-class model, but we can do multiple classes here. The portenta is also really powerful, so it's not really a problem. At Henk, so we actually use some of TensorFlow Lite for micro, but we compare, but we compile this with Eon, our own neural network compiler, to be much more efficient. So we run on anything with a C++, compiler. So no need for TensorFlow Lite to be ported to it. All right, so in the last 2 minutes, I want to do some tips. This was a model with just 100 photos, and that already gives you insight. So start collecting raw data directly today. That's the best way to get started. And don't just think of it as, don't just do cameras, right? Or just do images. We can also do audio, high frequency accelerometer data. Johan in a sheep costume last year was built on the same premise. So I think machine learning lets you tackle much higher value use cases. Stuff that your sensor could never see is now being able to see that. So really cool. Also, device duty cycle is incredibly important. So we do 50 milliseconds for inferencing and then 50 milliseconds to snap a snapshot. In the rest of the time, you can be asleep. So if you snap a photo every 10 seconds and classify it, it means you're 99% idle, which is great because then you can be in deep sleep and just wake up, snap a photo, go back to sleep again. So think of that way. Also, every time you classify something on device, you don't need to send anything to the network. You already win a lot because typically the power consumption of LoRaWAN devices is completely determined by how often you drive the radio. As said, this was on the portenta, but you just get a pure C++ library. It compiles on anything under the sun. So if you have a dev board and you want to apply some machine learning to it, go ahead, and we're happy to help here. And I'll leave a couple of links in here while I'll read through the last questions if there's anything. So one of the interesting things also is that we are launching on the 8th of January a embedded machine learning course on Coursera together with Sean Heimel. So if you're interested in that, keep an eye there, and you can actually do the certification on that and really build something amazing. We actually yesterday published a blog post on doing audio classification and relaying it to a Lacuna space satellite. So definitely another conservation project, but something you can build today if you have an LS200 dev kit. So with that, I think we're at the end of this workshop. I want to thank everyone. Yeah, let us know in the forums if you have any questions, and always happy to help. And I have no idea how to stop.